Welcome back to High Performance Computing. We have our lecture 5 today in the second part already of it. In the first part, we had essentially the idea about what actually shared memory entails, and we had a very nice longer MPI, let's say, revisit in order to understand the differences, to really understand that MPI is for message exchanges in distributed memory, while OpenMP has a shared address space for parallelization. So different threads use the same address space. You don't need message exchanges. You have just access to the variables and can use them in parallel threads. Obviously, that will raise issues sometimes where we need critical regions. That's what I want to explore a little bit more when we come to real parallel programming on this. But basically, in part 1, we had already an idea what OpenMP is, the standard idea of it, enabling portability, at least to some extent. Obviously, if the memory is bigger, you can do more. If the basically generations of HPC systems with the hardware underneath is basically newer, the direct performance will be not portable, but of course, the general approach, it will be basically compilable. And this is already the first good point. Different Boisley elements we have discussed with essentially having still some serial parallel forks and joins, which means that every now and then we have this master thread, if you remember, surviving, so to speak, every time this kind of fork and joining of parallel regions. And we will look into this now in the second part a bit more in detail on the C level, what that really means, how I do this with some practical examples. This also enables me to say a short, disclaimer that obviously this lecture cannot really entail all OpenMP elements. We basically run in the HPC centers around in Europe, at least basically everywhere tutorials which have a couple of days, so 3 to 5 days rather, is something where you learn much more of OpenMP from morning till evening. And this is an evolving standard, as we have seen with OMS, with PyComs, and so on, where we see even more generations of OMS are integrated into OpenMP. New ideas about task-level parallelism are entering the game. In a way, this was already sort of in OpenMP existing with the thread idea, but now it's extended to much bigger concepts, including, for instance, also accelerators. And that's something also we will look on in the end today, a little bit in the second part, but also, of course, when we think about accelerators in lecture 6, which is coming up in the next lecture. So fasten your seatbelt again for a new parallel programming language. Needless to say, we still have to think more and more in parallel, like we did with MPI, but here now we think about threads. We have it sort of a little bit easier of thinking that we have basically a shared address space where every thread can access to, read the variables and so on, and read the variables, basically write on them. And we have seen that loops might be an interesting candidate for parallelization. So this is something also what we want to look at. And the key idea of OpenMP inherently is also to make it a bit simpler, right? So maybe not to do lots of parallelization statements, to do all the programming and so on. Instead, we're using something called compiler directives to enable the compiler to change things in the application. That's a bit different than we had this in MPI. If you remember, in MPI, we had concrete functions. They did a broadcast. We had a concrete idea of separating between the different ranks, right, that we have in an MPI application. And if you're one rank, then you do one thing. If you're another rank, you do another thing. But here, the idea and the approach is a little bit different. We still want to have parallelization, but on a level that basically the compiler will optimize that for us. We just have to define with some compiler directives a couple of things to help, of course, the compiler doing this. And that's what we also will learn today. Another aspect is the wording. Think about that we think about lightweight threads here now instead of just processes when we think about this, and that we have this master thread MT, I call it here, that is then spawning all of these threads in this parallel regions or basically joining them again. Now, coming to the first hello world, I guess that's what you expected. What we also compare to MPI, we start with a very, very simple MPI application. Now we have a very, very simple OpenMP application, perhaps one of the most simplest one, where you see firstly the C code, the main operation in each of the C programs. This must be existing, and we had a printf statement, hello world. Obviously, that's what we need and want to parallelize. What you also see is that we basically have here an independence again of how often I parallelize this. This pragma OMP parallel is basically the well-known idea of the compiler directive here that we have here, instead of saying, I want to parallelize this for 3 times, make a for loop, and then I see how I can parallelize this in different threads, in different basically applications on the cluster. So here it's very simple. We just have basically a small compiler directive, and everything else needs to be steered outside. Outside meaning our job script. So you have here an export OP number of threads. That now steers, for instance, that we have 4 threads that we can use in the application. We could have used 5, but here we decided to have 4 for a certain reason, probably from the application. Obviously here we could choose more. It's a hello world. This is just a small, simple example, but this will now steer the number of threads that will execute these basically. And you see when they compile it and then execute this kind of executable, which we have compiled, then essentially 4 times hello world comes out. Very similar like MPI run with 4 processes, if you remember. However, here we talk about now shared memory. That's not obvious here. Of course, it's just still a parallelization simulation or demonstration of a printf statement. We're still not using any parallel variables or something. Just the same part of the source code, right, will be now executed 4 times by these different threads. And how it works is essentially that this one thread that is living here is entering this pragma statement and will basically spawn these 4 threads that are basically defined with the OMP number of threads. A more, let's say, elaborate example here you see now, when we basically extend a little bit the idea. So you have the overall picture of the hello world example. Again, you need an OMP header, similar that we had also with the MPI header, obviously. So to know about the operations then you can do. We want to have the number of threads and the thread ID. This is something which is quite interesting for us because it gives us a little bit, again, a comparison idea to what we had with size and rank, if you remember, in the MPI space, right? So again, if you want to have maybe a very smart application, you want to perhaps know how many threads there are and what role do I play as thread, right? So what role does a specific thread play? And for this, the thread ID, which is a local variable for each of the thread differently, is something, of course, which could be quite interesting in this. So it's kind of comparison to ranks and the kind of size of the communicator. But it's, of course, here not really the same, but the idea is basically the same a little bit. So coming to the idea, now that we have these defined, there's a certain private statement that you see in the TID idea of the thread ID here. This should be private. In other words, it's a so-called local variable for each of the threads. In other words, when you have now 4 threads available, every one of these 4 threads will have their own thread ID. And this may be useful because this should be probably unique. In order to get the unique number of the threads, you see OMP get thread number. Hence, we don't have only compiler directives, we still have also functions that we use in basically OpenMP. And here's the idea is, of course, within this parallel region that I defined with a pragma statement, right? You see that here. You basically have the idea of the sentinel to parallelize and fork now all these different threads, right? Where this is called the sentinel here, this pragma statement. But I want to do this, and then I want to know which thread I am. And this is now giving us the opportunity to extend the hello world a little bit more to say hello world from thread. And I do here basically the thread ID. So if you basically compare it a little bit to the rank idea, of course, we want to use the thread information or the thread ID to say only one particular one of these threads should do a specific other thing. So that's basically, we see here, let's say thread ID 00, our super master that is basically doing the forks and so on, and will be still working on the parallel region, will be entering in this, and then basically fills the other variable, the number of threads, with another OMP statement, OMP get number of threads, right? Which is the overall number of threads that I basically was given to by the job script. So, and of course, I will print that out so that we see the output. This will be only executed, although we're in the parallel region here, not four times if I, for instance, have 4 threads, but basically just once how many there are in the parallel region. Now, the modus operandi, how you basically now compile, is very similar. Of course, we need some adjustments we will talk about. You see here basically one example of this hello world again that we just had in the source code, and basically a little bit alluding to the idea that we had. It's not exactly the same source code, but captures the idea that we say from each of the parallel region, one thread says basically what is my specific thread number or thread ID out of the overall number of threads I have. In the same way as we did with MPI, we had compiled the C program using a compiler. And you see here the GNU compiler GCC, I can have a compiler option with -f OpenMP. And then the usual things, what I said, for more convenience of the names of the executable, I use -o hello threads of the hello thread C code. So then we have an executable that basically now was taken into account these pragma statements, right? So this pragma OMP parallel is basically already the hint that there's a parallel region, and this pragma statement don't have brackets. So basically it's just determined by this one statement. So there would be one statement in parallel, and the other one here you see hello again from your main thread is then the idea that we just have this once, because this is the only parallel region here, this printf statement. Hence, when we do and execute this, we basically have then the idea of seeing this just once in the main thread, but 4 times from which of the different thread IDs. And in this idea of work sharing, when we have this pragma statement, immediately comes to our idea that this could be now useful for many different areas. And specifically ones basically that we have in loops. We had already a couple of examples in lecture 3 on this, where we basically can have the master thread, and every time we basically face a loop, there's potential for parallelization. Of course, we have to program this a little bit in a way that is, also possible to be parallel, or maybe some of the loops are not even possible to really crunch down in parallel, but many of them are, depending on how you program it. And then afterwards you join it. You can have, however, also different sections that you want to do. Basically, that also works. You can have different parts of your parallel region, basically crunched or broken into different sections. It is also useful for implementing something we call this functional parallelism, what you have the different ideas, what you do in these different sections, where here are all basically doing the same idea, what's happening in the loop. Here you can explicitly say different aspects in the different sections. And one interesting aspect is perhaps when there's a very sensitive operation on some variables, for instance, single can also serialize a section of the code if necessary, right? Obviously, that is not so good because then we cannot leverage the parallelization always if you just do single constructs, but it's also sort of very specific way how you can here and there protect or basically work in your OpenMP applications. Here's a beautiful example of this loop parallelization that would just work beautifully, although we would have shared memory. In other words, everybody, every basically process that is then basically interpreted as a thread here in shared memory, because we have the same threads operating on the E, on the A and CB here. And this can be nicely parallelized, right? So this means because there's no dependency on the previous elements on the array, that we basically here multiply with a constant. And the constant is also important in that. So we can just crunch down this big loop from E1 to 1000 in 2 times 500 chunks. And with this having basically the execution time And this T doesn't mean the threads here. This means execution time, where basically the second execution time of using just 2 threads here would be smaller than the first one, where we just had 1 available. One example of how to beautifully and automatically, with this kind of compiler directive, we would be able to really, make this easy to parallelize. Here's a more elaborate example how this could now work when we have basically this simple operation of the addition of basically 2 vectors here. It's also something where we have to prepare this a bit wisely in order to basically have the variables in the sort of protected state and private state, and some of them as a shared state that you see here. And basically you see a couple of mallocs, which is now maybe not for every one of you obvious. It's anyway a simplified demo code, but here we allocate basically space of X and Y. And in order to then basically here do an addition on this, and you do, of course, this in a for loop. If you want to program this, you go through the different array elements from 0 up to a certain number of n, whatever basically the size of the array n is. That's something which we don't really specify. But X is then now basically given as the idea of always updating elements of the Y at the same basically index. So a very straightforward way. And you see already the color coding that I used also in the GPU idea. Here you have the same idea that basically in order to compute the X result, you can nicely do this index by index, right? You send just the zeros are relevant, the ones, the twos at that particular point in time. There's no dependency on everything else, which makes this so beautifully to be parallelized. All I'm saying here is then that, of course, if you want to do this, let's say with 3 threads, that means every thread needs his own E variable to say, well, I take care of the zeros, you take care of the ones, and you take care of the twos. When I have now 3 threads executing this. Very simplified example, right? But still captures the essence how that works in order to do this. And then basically have this in parallel executed, the pragma region, this kind of for loop. And then once you are by there, the X contains the overall result. And here's a little bit an idea again, when you think about why we're doing always a shared XY. So this means now I specify really in this loop that everybody shares, of course, the kind of X and Y's that we basically have initiated here. Obviously, this is just basically preparing the space of those. But of course, also in real applications, you would probably fill that wisely with some interesting numbers that you want to do. Here it just shows you a little bit how this works when you now do kind of parallelization constructs. And with this, it means that this private data that would be now the E in this example, think about it. Thread 1 takes maybe care of the 0 index. Thread 2 takes care of the 1 index, and thread 3 of the 3 index. And this is incorporated in the private data, while the shared data will be then the overall array. I just use then basically my index or the E from the loop in order to access my own part. What you also see is I don't program any of this. That basically is now taken care by thread 1, 2, 3. All I'm saying is pragma OMP in parallel, compiler, please do this, fork of a parallel region. And you see basically it's just one statement to do it in parallel. But of course, the inner part needs to somehow match what you have here in the pragma statement, and basically also enabling us, for instance, for the for loop to move through this as a private. But each of the work will be very independently performed. And of course, doesn't need to necessarily just having, one array part addition to another array. You think about much more complicated aspects, right? But the point is it's independently, and then you later on have the overall result. And you don't have to compute any of this. And it's already in memory, obviously, because everybody operates on shared memory, like this basically is suggesting here. So this is kind of beautiful to help the programmers really to do easy parallelization. However, you think about also that when you do this, be careful at what point in time maybe certain elements are executed. If you would have some other index that depends, for instance, on the index wrote before, and you have sort of a time dependency if you want, this wouldn't work really much. So you have to be there also careful what you put in the loop, not just put now every loop and say, oh, that could be beautifully parallelized. It depends obviously on the problem. And here's a good problem that we can parallelize, beautifully independently from each other. And I guess the meaning of this and the idea of that gets more clear. It's a simple for loop example. You can obviously now tune this example to different elements, which is part of the work sharing contracts when you have a much more advanced loop example, where you maybe have here another idea. You see that a little bit from the source code here, a certain chunk size. Now we're talking really about an array maybe of the size of n from the array, so much bigger and so on. Still, the idea of the chunks might be still applicable, right? For certain chunk sizes, I can still, parallelize all of this. And you see also that this is a kind of idea of initializing here the arrays. I basically have something to work on later on, but this is not done in parallel. That is, of course, all serial by the master thread. And only the pragma statement now opens up the parallelism. You see also you can have a nested parallelism, which is quite interesting for us. So where you can influence then certain elements. Here the idea is to have A, B, C, and the chunk now in this shared address space accessible. And again, as we know before, the private variable E. And the second nested parallelization that is now in front of a loop, right? It has, so you see the difference, pragma OMP parallel as a parallel region with the brackets, and pragma OMP 4 is basically now the loop parallelization I have here, right? So this is important to understand. So this would be executed in parallel for the loop and this as a whole region. And you see here essentially a couple of things which you can actually then steer from the more, let's say, optimization perspective. You can have a static order of who is getting the chunks to work on, which thread. So basically, it's a very static addressing of work constructs, if you want. So, and dynamic would be, first come, first served, more or less. When one thread is ready, basically with the execution, like task 1, for instance, it will be immediately again coming up to basically work on some chunks of the tasks that needs to be done by this chunk. So with this, you can have also a kind of way of influencing a little bit how this work is performed in order to steer a little bit the performance. And here you see also a more elaborate example of an advanced for loop that is here and there used in practice incredibly often. Because of course, having a full chunk is much more useful in parallelization, you see here, than always doing one little, index in that part. Hence, let's go and think a little bit about what else there are. The sections we discussed already roughly as part of this. Well, now the idea of doing in these sections different functions, different ways, basically how you want to work in the parallel region. Still, it is executed in parallel. You see that again, we have A, B, C, D here as kind of shared variables and a private E again, suggesting there's a loop coming. We have an overall region that is parallelizable with the sections, right? You see also pragma OMP is now sections and not parallel. And the sections are indicated by each of the different pragma OMP sections. And each of them go actually through a loop. But you see also the idea what they do. We said functional parallelism, meaning a little bit different functions would be executed here, different physics, whatever it is. And in this example, we just add and multiply the array, right? Which is in the different results of the C and the D array. And this captures nicely action, how you basically would now use the sections. They are similar in the execution. Maybe they can both use, of course, the information from the A and B arrays, but do different functions, very simplified here, but a good illustration of basically how these different blocks work in the section for these different threads, which will be executed alongside basically the job script that we define here. And there are different synchronization constructs as well. I was already alluding to this when you think about that many threads, let's say, they have a big OpenMP application, and the 20, 30, 40 threads all want to access at the same time X and also read from it and write from it. You can imagine something we called race condition around this variable X. This would not really work well. So you never know when is who is writing when. So there must be some idea how you can protect a so-called shared variable, right? And this is something where there's a specific construct called pragma OMP critical. However, this needs to be, of course, also taken seriously. Firstly, because obviously this means every other one is not allowed to enter this. Let's say you have many different threads that work in parallel in this pragma OMP parallel statement, 20 threads working on a problem on a shared X, maybe in one way or another, and then suddenly comes in pragma OMP critical. Then that means 19 threads are idle. You see this also in this particular one, where basically another one is just, everyone is only basically one thread is basically in this critical region, right? It has to wait until this first thread is really finished, and then the other one is coming, and then the other one that is reaching this. It's a bit hard to visualize concretely, but if you have 20 threads, you can imagine these 20 threads are serialized more or less, first come, first served to this critical region, and only one is executed now then at one point in time, this X, which is here very important because you see to define X, we reusing X, so reading from it, +1. And when you do this at different times, maybe someone is here modifying X for some respect, this would be very tough to do, and they all can now do this at any point in time. And this helps us a lot to work with race conditions on variables, which is, of course, in the concurrency that we have with a shared memory construct now possible. In distributed memory with MPI, that's not possible, right? Because I have basically no access to this memory. Basically there, I need to first send a message, do it in the buffer as we learned, send it over, and then the process itself is responsible of overwriting then this value. But it, so to speak, cannot happen by accident. And there's a similar construct, which is a single example, where basically the block of code that you see here, everybody's doing a setup of X, whatever that means. It's some pseudocode. And then the first thread that reads a single directive will basically execute this, and all other threads don't need to do this. Right? They maybe work on a very critical setup of input from Y for some reason we don't know here. And the illustration already shows that all others are being idle. Important it is to understand it's the first thread, not necessarily the master thread, that is coming to this and then executed it as single, just one thread allowed. In a parallel region still, right? So I still have my other threads. Pragma OMP parallel is around here as an example of the parallel region. And we basically do all the setup X as a team of threads. Then we're reaching this, and the team of threads has to sleep only one thread when one basically is going into this, executing this. And once this pragma OMP single is over, we perform all together the work on X and Y. So this is another idea of how to do synchronization, of protecting some variables perhaps from being overwritten, lost updates, or basically this race conditions I was alluding to earlier, incredibly important as well. Now, basically, what you immediately think about, it's a bit a shame if we lose always data from parallel region over these different serial regions. Again, we had this parallel region, it collapses to the master thread. Then we have another parallel region collapsing to the master thread, and so on and so on. So how we achieve a little bit sort of persistency between these parallel regions when we think about, basically our memory space again and all the different threads. And here you have a idea basically how that could work. When we think about executing this now one by one, where we have two parallel regions. You see here, this is the first OMP parallel, the private B, and the thread ID is existing. And then I would have basically a pragma, or to so to speak, the second parallel region, where I just have private the thread ID. Hence the B more or less is shared here. So let's look how that would execute, right? And what we do there. For instance, we can here set the thread private A and X, which enables us that basically the variables are replicated, and thread private as a private suggests again, basically each of the thread would have an A and X. That is very useful. So basically that means we can have this also then basically available in different parallel regions, as we will see. Dynamic threads are put out here for a while. It's more just for the demo character. Let's move into the first parallel region that we have here. We get the kind of thread number, a very specific one. And you see here the remaining output again to really differentiate now between this persistency I was mentioning, where we basically have an A as a thread ID, the B is a thread ID, basically coming to the idea then computing X with the thread ID, but meaning some specific idea how to modify it. And then you come to certain solutions in this particular idea, how you compute this here. It's like 1.1 times the thread ID plus 1. And then we give it out here, which is essentially the output you see here. So this is the first parallel region. That's quite well straightforward, but the second idea is now that, of course, I collapse here this parallel region, right? In other words, there's just the master thread available that is doing some work. This is here this interesting thing, the master thread is doing 0 work, whatever it happens. So let's kickstart another parallel region that we have here and get again the thread ID with the OMP number threads, and it's private, so that's okay. Note that we this time don't really have the B here, basically as we have here in the private statement from B, right? So then basically we would print off what basically happens here with the A and B when we think about this. And because we don't really preserve this in the thread private, we basically see that this is basically all 0, right? So this is something where you can then think, if you give it out here, you see as A, B, X, and equals then the D that you have here. And you see what we give out is then the thread ID, which we have obviously as a private variable. We have the A variable and then essentially the B variable, and then coming out with the X as the result. So hence, this is something where you can see a little bit that the kind of idea how you keep it in the persistence helps here a little bit as a toy example to understand how that would be computed. Obviously, there's no determinism. Still, you see here thread 0, right? In this thread 0, 2, 3, 1, we have to be careful to think about 3, 1. That's similar like the ranks in MPI. So because we're talking about the output on the screen, there's not really always the same thread, number here that is equaling this, but can also see that A, B essentially in the outputs then later have essentially then these different values. And yeah, basically because we don't initialize A here, right? This is coming still from the idea that we initialized here, A, and it was thread private. So this means that it was replicated and it basically was kept. So that's why we have values here for A, right? To just again come to this. Of course, B was also the thread ID in the first part, but it's not thread private as we see here. Hence, it loses all the information because in the second parallel region, we also don't define B anymore. And that's why it's 0. And obviously then basically the X, because it's thread private, we also don't initialize that here, has still kept the results, right? Which is quite nicely as well here. And all of this is basically the point, making a bit persistent to not always initiate maybe certain elements of this thread and variables. But let's carry on and go a bit quicker, maybe through some of the examples I have here with OpenMP and so on, pragma OMP statements, where you have then a certain idea of doing something like you already know from the MPI reduce operation. So you can actually combine here an idea of an operator. Different operators are allowed. You see here, common is of course a plus, but also multiplication, etc. The maximum of the array we discussed once. So here you see also that you can nicely combine this OMP parallel statement, not only with the shared and private variables or the schedule that we discussed with the static distribution of the threads of work or chunks, also to do some reduction inherently that basically saves you again from programming something that you don't need to do. Here we're saying about the result should be in the end all basically leading to one final big result that is added. Although basically we see here it will be computed in parallel first, and then the end will give us all the results from all the reduction over all the different parts of the array that we have done. So in the end, because it's also a vector, vector dot product example, if you want, this is even just the scalar, so just basically one float that can be given out. More advanced applications that we will also touch on later is, for instance, here the example of P, which is another idea of using here a pragma OMP parallel statement with a private operation E, suggesting the loop iteration, and then a schedule dynamics. So every time a chunk is finished, some other operator, some other thread will take the operations. And here is a little bit alluding to how basically the idea of calculation of P works. It's alluding to so-called Monte Carlo methods. You just have to do repeated random samples of these dots that you see here in the space to actually calculate how many are in the circle and how many are out of the circle. And as we know a little bit about the overall idea, essentially of a kind of overall circle, we can use this information over time to compute essentially here the value of P. Important is this Monte Carlo sampling. You do this incredibly often. So this means you approximate it more or less through the number of runs that you have. It's a very known example, basically, how you use basically essentially Monte Carlo methods for this P estimation. And that's not the point here. The point is more that you can, of course, now parallelize this beautifully because each of the different dots is essentially not really dependent on the other. So we basically can do number of these Monte Carlo elements with a hit and non-hit, hit and non-hit, which is given by this particular rule that we have here, basically given. So this is something which we can, of course, also beautifully parallelize because it's an independently parallel example, right? It will count the number of hits, and basically with this influence the estimate of P with these hits, and then basically come to the value over time. And you see why over time is important with 3.2, which is not P, but with the number of runs, 100,000, 10,000, iteratively doing this experiment, you come more and more closer to the P operation. Another example why elements which are nicely parallelizable in these loops, certain things, certain operations are really a perfect example of using it with OpenMP. And the way how it's parallelized, you see it's just one statement, right? It's also interesting to see from the effort of parallelizing this. Obviously, this inherent rule is already in a way nice for us when we transfer it to the real implementation here, that it is beautifully parallelizable. And this helps us here, of course, to do that. But in the way how you really, as an application developer, now think about it, the real parallelization of that is instead of doing it, really this number of iteration times, which could maybe on a normal laptop mean hell a lot of time, but here on a big supercomputer where you can have lots of threads, maybe executed very much quicker. And of course, you can imagine that exactly this is happening in solvers and simulation sciences based on basically numerical methods, using known physical laws. For example, the heat dissipation that we had in the room. We have lots of these iterations always, right? We always have this after so many iterations, it looks like this. We have here the heat in the room after 200. We had talked about the stencil methods, where we basically also here see again, have this in shared memory, so I can easily access it. And what I do is I need basically variables that captures a space of the T0 before I will basically overwrite my T1, right? So the next iteration, of course, in the heat of the room depends on the variable state from all my neighbors. And I need this input at the specific time before I go to the next iteration to recompute it based on the inputs I have from my surrounding neighbors. And with this, you have another iteration and another and another, right? And this is, of course, with OpenMP possible as well. You just have to make sure that you can parallelize this nicely and have to see basically how this is now fitting into memory. If you have a big application program, this might be much more tougher to do actually. Then towards the end of the lecture, just some selected comparisons with MPI. I think many of this I touched upon already. We have ranks versus thread IDs. We have the load imbalancing issue as well. There could be idle threads. There could be the problem that I do just critical regions in OpenMP, right? Which of course means then others have to wait, right? This is also something which is very stupid if you see basically this critical regions. And here's a load imbalancing at all. One thread is just, computing still and others wait and are idle. All of these problems are the same. A little bit different is the synchronization in terms of direct variables in the shared memory space, which you have to take care of, which you otherwise have to explicit send over. So it's automatically a little bit protected if you want through this mechanism of send. You can actually monitor and debug and do performance analysis on OpenMP codes that you see a little bit here with the total view debugger. This is possible to really look at the variable state. And then at the end, let's look a little bit how it worked with programming GPUs. But we also touch on this a little bit on lecture 6, so it's very short, thinking just that the idea of parallelism that we discussed with master thread forking several parallel regions and then joining again reminds us a lot how we would program GPUs, right? There would be basically some computation in the CPU, and some point in time I want to use the accelerator and doing things in parallel. Hence, there's a language called OpenAC, which is basically for accelerators, doing very similar ideas of this pragma statements, but extending these to the idea of accelerators, where you have to, again, copy out the data to the device, and then basically have the kernel operating on the GPU. And then you can do the same on the parallel loop, outsourcing this to the device memory and the accelerators. So this will be more a topic for the next lecture. Hence, just the motivation for lecture 6, when we talk about accelerators way more. And we already had the algorithm here. Think about that this is really used in practice. Also that people really combining this in hybrid applications, as we have seen with this data set here, which is based on MPI and OpenMP, and with this having even better performance than just using MPI. But actually to program all of this is quite complex these days. And you see here, we have to have a certain number of threads that we basically use and have in our job script for this HPDBSCAN operating. We have the number of nodes that gives us a normal kind of CPUs, a more advanced idea how you allocate resources, something which we will also more use in the second part of the course, and how basically now in this source code that you have is actually the idea of pragma MP elements as well, right? So it's not only an MPI code where we do some elements between the different nodes that we will have. Also within each node, we try to leverage the shared memory to do some local clustering, if you want, of this in order to then merge the bigger results later, using also MPI to merge the halos again. So hence this is really used in practice. Another application is here for rendering, a ray tracer with OpenMP, which is quite intuitive to watch. And with this, I really want to stop today. I think it was a lot already introducing you to OpenMP, an interesting topic, and we will continue next time. So see you then.